Hi dear students, this is the second part of the fourth module EST 100 Engineering Mechanics. So in the first part we have seen the basics of the dynamics of motion. Now we will discuss in this presentation we will discuss motion with uniform acceleration. Motion with uniform acceleration means throughout the motion the acceleration is going to be constant, it won't change. That is the meaning of motion with uniform acceleration. Here acceleration will not change with respect to time, that means a equal to acceleration a equal to constant. From the fundamentals of the mechanics, we already have rate of change of velocity with respect to time is acceleration, dv by dt equal to a. Now we can write it as dv equal to a dt, and on integrating, integral dv it is equal to a into integral dt. That means integral dv is nothing but the velocity v, and a is constant that we can take outside the integral. Therefore after integration we will get v is equal to at plus c, where c is the constant of integration. Now we want to find out that constant value. For that we are using the limit at t equal to 0, v is equal to u. As we know, when before, just at the time of starting t is equal to 0, the velocity is nothing but the initial velocity. So v is equal to u at t is equal to 0. Now substituting on the above equation, u equal to 0 plus c implies c is equal to u. Now substituting for that constant c, we get v is equal to u plus at. This is one of the fundamental equation used in the field of kinematics with uniform acceleration case. So note down that equation. Derivation is not that much important, I think, but still this equation is very important. Everywhere we will be using this equation. That is the first fundamental equation that we have derived. Now move on to the second equation. Here from the definition of the velocity, we have ds by dt equal to v, rate of change of displacement with respect to time equal to velocity. But from the earlier equation, we have just equation that we have just derived early, that is v is equal to u plus at. From this equation we have v is equal to u plus at. Therefore the above equation can be written as first equation, that is this one. This equation can be written as ds equal to v dt, and instead of that v we will substitute this one. Therefore the equation becomes ds equal to u plus at dt. Now go for the integration. Integral ds equal to integral of this entire term, that is integral of u plus at dt. Split this term into 2, that is u dt plus integral of a dt. So we will get left side it is integral ds, that will become s is equal to, first term it is integral of u dt, that will become ut, plus second term it is integral of a t square. A is constant, can be taken outside the integral. Therefore t dt, that is t square by 2 will be the integral, will be the integration. T square by 2 will be the answer after integration. So s is equal to ut plus a t square by 2 plus c, where c is the constant of integration. Here also we want to find out the value for c. So we want to substitute the conditions, boundary conditions, or whatever it may be. So to find c, at t is equal to 0, s is equal to 0. That is one condition. At t is equal to 0, s is equal to, since time equal to 0, the body did not have started to move, so displacement will be 0. That's why we are using that condition. So substituting for s is equal to 0, 0 equal to ut, t is 0, therefore that term also becomes, this term also becomes 0. Here also t term is there, since t is 0, that term also vanishes. So 0 equal to c. So c equal to 0 you will get. Finally substituting for 0, final equation will be s is equal to ut plus half a t square. So this is again the second fundamental equation that we are going to use in the field of engineering mechanics, kinematics of kinematics field. Okay. Now we want to derive the third fundamental equation, that is this one. From the definition of acceleration, first we have considered the definition of velocity. Then first we have considered we have derived this equation from the acceleration itself, definition of acceleration itself. The second one we have derived from the definition of velocity, and third one again we are going for the acceleration equation. A is equal to dv by dt. Acceleration is rate of change of velocity dv by dt. This can be rewritten as dv by ds into ds by this can be rewritten as dv by ds into ds by dt. That is, we are multiplying and dividing the entire term with the ds. So ds and ds cancel. Finally, it will be equal to dv by dt. Same thing will be coming. Just I am multiplying and dividing with the ds. So a is equal to dv by dt. That is first term as such. dv by dt equal to dv by ds. This first term dv by ds into second term you see ds by dt. It is ds by dt. ds by dt is nothing but velocity. So entire term becomes a is equal to dv by dt, that is equal to dv by ds into v. Now we will take this second term and third term, that is ds by dt equal to now we will take the a is equal to dv by ds into v. Now initially a was dv by dt, now it has changed to dv by ds into v. Therefore a ds equal to v dv. A ds equal to, that ds is taken to the left side, so a ds equal to v dv. Now on integration, a is constant, therefore we can take it outside the integral. So a into integral ds equal to v dv, integral of v dv, and the we are giving the limit. Integration is from u to v. Initial velocity is u and final velocity is v. So on integrating, v dv will become v square by 2 and the limits are u and v. Left side it is a into integral of ds is s. So a into s equal to v square by 2 into v square by 2 limit u to v. Now substituting upper limit and lower limit, the equation reduces to a into s is equal to v square by 2 minus u square by 2. Therefore 2 can be taken to the right side. 2a is equal to v square minus u square. And finally this equation is reached, that is v square minus u square equal to 2as. This is the third fundamental equation used in the field of kinematics. Okay, these three equations you must do by heart, that is v is equal to u plus a, v is equal to u plus at, s is equal to ut plus half at square, and v square minus u square equal to 2as. Here u is the initial velocity, v is the final velocity, t is the time taken to travel from one position to another position, and a is the acceleration. Okay, so we have derived the three equations. The derivation is not that much important, but this equation is very much important. Please remember this equation. The important equation for rectilinear motion with uniform acceleration are v is equal to u plus ac, u plus at, s is equal to ut plus half at square, v square minus u square equal to 2as, where u is the initial velocity, v final velocity, t time taken, and a is the acceleration. Now we will look into a small problem, direct problem. Just can ask for 2 mark or 3 marks, something like that. Just to understand the concept, that's only I am giving this problem. The position of a particle moving along a straight line is defined by the relation x equal to t cube minus 3t square minus 9t plus 12. Determine the time taken by the particle when its velocity becomes 0. That is the question. So this particle is moving along a straight line. The position of the particle moving along the straight line is defined by x. That means x is the displacement. So x is given as t cube minus 3t square minus 9t plus 12. Now we know velocity is nothing but dv by ds by dt. Here actually x is s, displacement. So velocity will be dx by dt. Differentiating displacement with respect to time, we will get the velocity. So just differentiating that x term, we will get first term it is t cube, so it becomes 3t square. Second term is 3t square, so it becomes 6t minus minus 3t minus 6t. Next term is minus 9t, differentiating t, that vanished, minus 9. Last term is constant, differential of constant will be 0. So the entire term velocity is equal to 3t square minus 6t minus 9. That is the velocity v. Now what we want to find out is determine the time taken by the particle when its velocity becomes 0. So what we want to find at the after sometimes the velocity is becoming 0, so it is deceleration case. So from a particular velocity is continuously decreasing, so finally velocity is going to be 0. So we want to find out that time to velocity to become 0. So we are substituting v equal to 0 in the above equation. So v equal to 0 implies 3t square minus 6t minus 9 equal to 0. From that you can find out the value of t square minus 2t minus 3 equal to 0. That is an equation. second degree equation, we can simplify t minus 3 into t plus 1 equal to 0, or we can do it in the calculator, whatever method it may be. Anyway, after solving, we will get t is equal to 3 or t is equal to minus 1. Since it is second degree equation, you will have two equations. First value, two value. First value is t is equal to 3, and second value you got is t is equal to minus 1. So t is equal to minus 1. Negative time is not practically possible. So we will take the positive value, t is equal to 3 seconds. So within 3 seconds, the velocity of the particle will become 0. That is what is shown there. Now moving to the second problem, sample problem, direct application of this fundamental equation. The problem is two cars are traveling towards each other on a straight lane road at the velocities of 12 meter per second and 9 meter per second respectively. So two cars are traveling on a same road, but opposite in direction. One is having a velocity 12 meter per second and the other one is having velocity 9 meter per second respectively. When 100 meter apart, both driver realize the situation and apply brake. Once they are 100 meter apart, they realize that there is a possibility of collision, therefore both applied the brake. They succeeded in stopping simultaneously and just short of colliding. Luckily they succeeded in their attempt, and just before collision both stopped. So finally both are in touch, both vehicles are in touch. So we want to find out, assuming constant deceleration for each case, determine time required for cars to stop, deceleration of each car, and distance traveled by each car before slowing down. These are all quantities we want to find out. Now looking into the solution, let A be the position of one car and B is that of the position of the second car when drivers see each other. So distance between A and B should be 100 meter. At that time only they realize. So A is at this position, A is at this position and B is at this position, and this distance is 100 meter. So at this time they are starting to apply the brake. After applying the brake, let them meet at C. After applying the brake, A has traveled this much distance and B have traveled this much distance. At point C, both the vehicles met. Okay. So total distance is 100. Let AC equal to x. We are taking this AC distance as x, then automatically the distance BC will be 100 minus x. That is total distance is, since total distance is 100, the remaining distance will be 100 minus x. Now considering the motion of the first car, u is equal to 12 meter per second, that is given in the question, and v is equal to 0. Since first car means u is equal to 12 meter per second, initial velocity was 12 meter per second, and why we are taking v is equal to 0 is just at the point of collision they stopped, so final velocity will be 0. So v is equal to 0 and s is equal to x. That means this is our first, A is our, from the vehicle started from A is the first body. So from here it is first body is going, so the distance traveled before stopping is x meter. Similarly, let alpha 1 a1 or alpha whatever it may be, let a1 be the acceleration of the first body. We are assuming a1 is the acceleration of the first body. Remember here it is not acceleration, it is deceleration, so you have to consider a negative side. So from the equation of motion we have v is equal to u plus at. Here v is equal to 0 and u was 12. So equation becomes 0 equal to 12 plus a1 into t. A1 is, from this equation you will get a1 equal to minus 12 by t. From equation v square minus u square equal to 2as, that is the second fundamental equation, we have v square v is 0, so 0 square minus 12 square equal to 2a1 into x. From this equation you will get 12 square is minus of 12 square is minus 144, that is equal to 2 into minus 12 by t into x, or x is equal to 60. This is one equation that you got, x is equal to 60. Similarly, consider the motion of the second body. Here for the second body u was 9 meter per second, same thing, v is equal to 0. Finally both bodies going to stop, or vehicle is stopping, so v is equal to 0. We are assuming second body acceleration equal to a2, time is equal to t second. Both will have traveled took the same time, t will be same for both. So s is equal to 100 minus x, because second body has the distance traversed distance 100 minus x. Now from the equation of motion we have v is equal to u plus at. Here we will get 0 equal to 9 plus a2 into t. From that you will get a2 equal to minus 9 by t. Similarly, v square minus u square equal to 2as. We have the equation. Substituting on that, you will get 100 minus x you will get 100 minus x equal to 4.5 t. So this is another equation. So initially you have x is equal to 60. Here you have 100 minus x is equal to 4.5 t. Solving this, you will get x is equal to 57.47. T equal to 9.524 second, and alpha 1 equal to minus 1.26, next one 0.945, and x is equal to this much meter.